We are dealing with the last paragraph for this segment. A block of mass 1 kg is released from rest at the top of a rough track. The track is of circular arc of radius 40 meter. The block slides along the track without toppling, and a frictional force acts on it in the direction opposite to the instantaneous velocity. The work done in overcoming the friction up to the point Q, as shown in the figure given below, is 150 joule. So the first problem that is asked is the magnitude of normal reaction that acts on the block at the point Q, and the next one is the speed of the block when it reaches the point Q. So if we consider this particular problem, so I am drawing a magnified version of this diagram first of all. So this is the magnified version which we are dealing with over here, and this is the line which is joined from the center, and this is regarded as point Q over here. So this angle is marked as 30 degree. So over here, if I consider something like this, so then the weight of the block mg is acting in the downward direction like this, and the speed which it is having over here is equal to v, which is the instantaneous speed. So if I break the component of mass m, so the component of mass m can be broken in this direction, which will become equal to mg cos 60 degree. Why? Because this angle is 90, this one is 60. So this one will also be vertically opposite angle, that is equal to mg cos 60. And apart from this, because of the instantaneous velocity v, a force that is acting in the outward direction will also be mv square upon r. So, and both of them will result in the creation of normal reaction force N, which will be directed towards the center of this circular track. So from here I can write the expression that the normal reaction force N can be written as mg cos theta plus mv square upon r. Now in the next part over here, I am breaking the component of the distances that we have traveled. So this is equal to 40 meter, which is mentioned in the problem, which is the radius of this particular circular track. So this height which it is lowered by, that is this height, is equal to 40 sine 30. So this height is equal to 40 sine 30. So there will be two components. This component will be 40 cos 30, and the other component over here will be equal to 40 sine 30, which is marked as h in the diagram. So the loss in potential energy. So as the block moves from the upper edge to this point Q over here, so the loss in potential energy, can be written as mg into h. So this over here will come out to be, the mass of the block is 1 into 10 into h is equal to 40 sine 30, that is half. So this is giving to us equal to 200 joule. Now this is some part is spent in overcoming friction. So work done in overcoming friction. So work done in overcoming friction is equal to 150 joule. So the residual energy is in the form of kinetic energy if we use work energy conservation or energy conservation theorem. So we say that therefore kinetic energy of block will be equal to 200 minus 150, that is equal to 50 joule. And we can say that this is equal to half mv square, which is equal to 50 joule. or from here I can take that mv square is equal to 100. Now in the problem we are asked to find mg cos theta plus mv square by r. So therefore the normal reaction force which the problem is asking is equal to mg cos theta plus mv square by r. So if we start putting the value, we have this is equal to 1 kg into 10 into cos 60 is half plus mv square is equal to 100 and radius is equal to 40. So this will give us the normal reaction force which we are looking for, and it will turn out to be 7.5 Newton. So if we look at the options, so the answer is option 1, that is 7.5 Newton is the magnitude of normal reaction force that acts on the block at the point Q. Let us deal with the next problem. So the next problem is asking the speed of the block when it reaches the point Q. So over here we have already calculated this from this expression that half mv square is equal to 50. So if we use this expression, that is half mv square is equal to 50. So from here I can take that half mass is equal to 1 kg into v square is 50. So v is equal to square root of 100, that is equal to 10 meter per second. So in this case we get the answer equal to 10 meter per second. That is option B is correct for this particular problem. So with this we come to an end of the problem solving session for work energy theorem.